Okay, hi everyone, I'm Reshma, and along with me we have Jeffrey, who's going to be presenting the second half of lecture portion, and we also have amazing supporting leaders with us. So this is our exam 2 SSC review. Main concepts, main topics we're going to be going over is Chapter 4, which is periodic trends, and then Chapter 5, which is more on molecular and empirical formula based. So if you guys have any questions as we go through this review, feel free to unmute or type in the chat. Okay, so the first concept that's very important for periodic trends is understanding what effective nuclear charge is. So it's also known as Z effective, right? It's basically the net positive charge pulling the electrons towards the nucleus. So the main thing we want to understand that is it's an attraction. So the stronger the attraction is, the stronger the Z effective is, the stronger the effective nuclear charge is. So knowing this and knowing what shielding is, can y'all tell me what is the relationship between shielding and Z effective? If we increase the amount of shielding, how does Z effective change? Awesome. So for example, if we go down the periodic table, right? Let's say, for example, group 2, as we go down, we have increasing shielding because we have increase in valence shells. So there's going to be decreased pull or attraction, meaning decreased effective nuclear charge. So atomic radius is the total distance from the atom's nucleus to the outermost orbital. So similarly, what will be the relationship between atomic radius and Z effective? As we increase the atomic radius, what will happen to Z effective? Perfect, yeah. And another way, easier way of thinking about it also is as you go down the period, the atomic radius obviously gets smaller because you're adding electrons to the same energy, the shell, but you're increasing the number of protons, meaning you're increasing the positive charge, but you're adding electrons on the same shell. So there's increasing Z effective, but your radius itself is decreasing as we go down the period. Okay, so we will also want to understand the concepts of ionization energy and electron affinity. So ionization energy, it's very important to understand, is the amount of energy required to remove an electron, versus electron affinity is a tendency to attract an electron. So as atoms get smaller, think about as we go down the period, what happens to our ionization energies? Is it going to take more energy to remove an electron or not that much energy to remove an electron? Perfect. As we go down the period, the atoms are getting smaller, right? The radius is getting smaller. The radius is getting smaller, there's less distance between the positive nuclear charge and the valence electron. So there's stronger pull. There's stronger Z effective. If something has a greater attraction, it's going to take more energy for me to remove an electron and oppose that attraction, right? So as we go across the period, the ionization energy increases. What happens to electron affinity, the tendency to attract an electron? So if we think about as we go down the period, right, there's greater attraction. Yeah, there's greater attraction. So there's greater Z effective. So we're actually it's going to get a little bit easier to attract another electron. So ionization energy trend and electron affinity trend are the same. They both increase as we go across the period. Okay, so we also need to understand how to write electron configuration ions. So we know cations, there are two types of ions, right? Cations and anions. So for cations, it's going to be positive charge. So I'm going to remove the electrons first from the p orbital, the outermost p orbital, and then s, and then d. So whenever we do practice problems, you're going to get more of understanding of actually doing this and writing the electron configuration of ions versus just the neutral state. So this is a sample question. So the electron configuration of calcium 2 plus is the same as that of argon, and they both have the same number of electrons. So what can we say about both of these? They're both perfect isoelectronic, meaning they have the same number of electrons, the same electron configuration, but they are differing elements. So what is the electron configuration of Ca2 plus, calcium 2 plus? So we know Ca regularly is going to be 1s2, 2s2, 2p6. What is your question, Emily, about AR? Okay, perfect. So regular Ca, calcium, is 1s2, 2s2, yeah, 2p6, 3s2, 3p6, and 4s2. But whenever we have calcium 2 plus, meaning we have removed 2 electrons, there's a loss of 2 electrons, we're going to take away the outermost valence electrons, which are in the 4th shell. So we're going to take 2 away from 4s2. So we're only remaining with, we already have in the chat as well, 1s2, 2s2, 2p6, 3s2, 3p6. So argon and Ca2 plus both have 18 electrons. Is that your question, Emily? Is that why you were referencing argon? Okay, awesome. Okay. So another thing we need to understand is ionic radius. So remember, there are two types of ions. You have a cation and then you have anions. So cations are positive. So they've lost an electron. And so, so if they ask shorthand, you can just write it as AR, but most likely they would want you to write the whole thing because they're trying to test your understanding of there's removal of electrons in the outermost shell. But they're both the same, right? Ca2 plus and argon. So you want to see what the choices are, what they're asking you. Okay, so cations. Okay, so for cations, there's a loss of electrons, so the shielding is no longer as strong. So you just have greater attraction, and so your radius is going to be much smaller. So its radius is going to be much smaller. Versus we have an anion where an electron is added. You have greater shielding now, and you have further repulsion. So there's actually going to be an increase in size of the atom because the attraction is not going to be as much. So an easy way to remember this is this figure right here. The more electrons that you remove, the greater attraction there is with the positive charge nucleus. So the cation is actually going to be much smaller than a neutral atom or an anion. So knowing that, which one is smaller, Cu or Cu plus? Cu plus, right? So why is that? Because for Cu plus, there's an loss of an electron, there's greater effective nuclear charge, thus greater attraction, thus the ionic radius is smaller. Okay, so this is a summary chart that's very helpful. Z effective, atomic radii, ionization energy, and electron affinity. As you go towards the top corner, Z effective, ionization energy, and electron affinity all increase, and your atomic radius all get smaller. And the complete opposite when you go all the way down. So main thing is you go across like this, and then you go up the group. That's basically what the diagonal means. Okay, so another important concept is understanding how to write Lewis dot symbols. The next chapter, you'll go more in depth of drawing Lewis structures for more complicated compounds, but this is just for simple elements. So, for example, this is Si, which is silicon. Main thing is you want to calculate what is the number of valence electrons. So, silicon is located right here, right underneath carbon, group 4. So I know it should have 4 valence electrons. And so main thing is you don't put 2, and keep going. You put 1 valence electron on each side, and then if you have more, you add it into another clockwise or counterclockwise manner. Okay, so it's also important to understand the difference between ionic and covalent compounds. So simple covalent is a formation, a bond between two nonmetals, versus ionic is a bond formation between metal and nonmetal. So we have here is Cl2. They're both nonmetals, so it's a covalent bond. So what about NO2? What kind of compound is this? Perfect. It's a covalent. Nitrogen and oxygen are both nonmetals. Okay, so now I'm going to start sharing, and Jeffrey, take it away.
Sounds good.
Yeah, do you guys have, yeah. If you have any questions, feel free to type it in the chat.
Hey all, my name is Jeffrey, and I'm going to go ahead and go over the last content, chapter 5 of this of your exam. So chapter 5 starts off with a little bit of nomenclature. The rules are a bit convoluted as there are a lot of different compounds to remember, but I found a chart that kind of sums up everything, so we're going to go through it together and as well practice with some problems. So first, when you have a named compound, what I like to do is that I like to name the type of compound present. So if it's ionic, covalent, or an acid, then it kind of gives you a clear distinction of what to do. But going on to the flowchart, let's start off with if there's a metal in the compound. So if there's a metal in the compound, and you want to check if there's a transition metal. Let's start off with there's no transition metal. So let's say this is like group 1 or group 2 metal, like calcium or sodium. Group 2 elements, if you have a metal or nonmetal, this is what we call a ionic binary compound. So the way you name this first is that you first name the metal, and then you name the nonmetal second, and change the ending to "ide." So for instance, if we give an example, let's say that we have something like okay, so let's say we have something like NaCl. Notice how there's a metal and a nonmetal in this compound. So to follow the naming conventions, you just say that this is sodium chloride. Okay. Next, if there are 3 or more elements, such as a metal and a polyatomic ion, it's going to be an ionic ternary compound. And what you do is you name the metal first, and then you name the polyatomic ion second. And you don't change the ending to "ide." For instance, if we have something such as NO3 and ANO3, notice how this has 3 or more elements, and one of them is a polyatomic ion. So you would just name the first sodium, and then you name the polyatomic, which is nitrate. Next, if we go over to if the metal is a transition metal, we count the different elements. So if there are 2 elements and there are transition metals and non-metals, it's an ionic binary compound. And what you do here is that you name the transition metal first, determine the charge of the transition metal and write as Roman numeral after name, and then you name the nonmetal second and change the ending to "-ide". So what is an example of this? So for instance, if we have something such as FeCl3, well, let's take a look how to determine the charge first. So it's really easy for you to say, oh, this is a 1 charge because it has a 1 subscript. Well, that's not necessarily the case. So what I like to do in these problems is that to determine the charge of the transition metals, we have to do this because transition metals, they can occur in one or more like states. So in order to do this, what you do is that what I like to do is I write the element, right? FeCl, and then I write the compound again, so as it's written. So FeCl, right? And then what I like to do is I cross the charges. So what I mean by cross the charge is I put this 3 up here. I'm gonna write this as 3. And then since there's only 1 right here, there's a 1 right here implied, I'm gonna put a 1. So we know that the oxidation state for iron in this case is 3, and the one for chloride is 1. And the chloride one you can kind of deduce. The chloride you can kind of deduce because it's in group 7, so you can say that it has a -1 charge. So going back to our problem, we have the iron 3 chloride. Oops, it's not 3. Iron 3 chloride. So let's move on. So if we have 3 or more metals, we have a transition metal and a polyatomic ion. This is going to be an ionic ternary compound. So what we do here is that we first name the transition metal, determine the charge of the transition metal, and write as Roman numeral after name. And then we name the polyatomic ion second, but you don't change the ion to "-ide" this time. So an example of this would be Fe3. Just realized that the 3 was supposed to be in here. There you go. Okay. So figuring out the charge as the tip we did last time. If we uncross the charge, we'll see that the 3 belongs to the Fe, and then the NO will have a -1 charge. And you know this already because nitrate has a -1 charge. So what we can do is that we can say that this is going to be iron 3 nitrate. Okay, any questions so far? Yeah, excellent. You guys are doing awesome. Cool. So is there a metal in the compound? So what happens if there's a metal in the compound? Is the first element hydrogen? No. If you count the different elements and there's only 1 element, it's a diatomic molecule, and you just name it. So the acronym I like to use is Brinkelhoff. So Brinkelhoff is bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine. And those are all the diatomic molecules, as they naturally come in 2. So if the first element is hydrogen, yes, then it's an acid. So a little exception to this. Usually acids, they're found in aqueous states. So on your test, if it says HCl, AQ, then that's as acid. But if it's HCl like solid, what would you do is that you just name it as a just hydrogen chloride. So the H element is the hydro root. If it's an H plus an element, hydro plus the root anion plus ic acid. So instance, if I take this and my root anion is like Br, so if that's the case, then what the name of an acid calling HBr is going to be hydrobromic acid. So next, we have H in a polyatomic ion. If the polyatomic ion is an 8, the root anion is an ic acid. So let's take an example. We have HNO3. So this is a nitrate, right? When you name the diatomic molecule, would you just say bromine? Yeah, I think so. Yeah, just a bromine molecule. Yeah, that's a good question. So if you have HNO3, for example, would you name it, since it's nitrate, you would just say that it's nitric acid. Notice here that NO3 has a -1 charge, right? And also the H is a +1 charge. And that comes out to balance to make a neutral molecule. So whenever you're writing compounds like this, it's important that you balance the amount of H's so that it's balanced with the charge. Let's say, for an example, we have SO42 minus, right? And we want to make a acid out of that. What you do is that you have to add the H, right, in front of it, but you can't just leave it like this. What you need to do is that you need protons to balance out the negative charge. So making a compound of that, you get H2SO4. Yeah. And if you have a polyatomic ion in ite, you would take the root anion and then take the S acid. So if I wanted to make SO32 minus acid, for example, that would be sulfurous acid. If you have any prefixes like hypo or per, hypo means below the S, and then per means above, you would just like add it on there. So example, if I have something such as HCl4. So ClO3 is the 8, so that's chlorate acid. I mean, that's just chlorate, right? So one more oxygen is going to be what we call per of it. So this would be perchloric acid. Anyone have any questions on that? Okay, so next we have, if we're going back to the count the different elements part, 2 elements covalent binary. So name, if we have 2 elements, then we are going to name the first element using prefixes, except for mono. And this means that we indicate how many of each element is in the compound. And we do this only for covalent compounds. And what's the difference between covalent and ionic, you may ask? Well, ionic, you usually have the metal and the nonmetal, but covalent, you have 2 nonmetals. For instance, if we have something such as N2O6, what we do is that if we look down here, we use 2 prefixes. So we have 2 for di, and then we have 6 as hexa. Well, what's going to happen is that we're going to name this dinitrogen and hexoxide. Okay, so here are some helpful tips. These are the polyatomic ions lists that you guys should memorize. This is really important that you memorize because it doesn't go away. You'll see this in further chemistry classes, so I highly recommend making flashcards or writing them out and drawing them as well. Here's another helpful tip, how to find a transition metal. What I like to do is I like to do the crisscross method, but if you like this method too, where you find the charge of the anion, you determine the charge of the transition metal, and then you say that the transition metal is always positive. There's also a worked out example here. If you like that method, then go for it. So answering your question, Michael, for the past part, the per, so per is used to indicate 1 more oxygen than the 8th molecule. So if you remember, ClO3 minus is 8, right? Chlorate acid. So just chlorate. So when you have 1 more O, you have O4, so which is going to be perchlorate. Does that make sense? Okay. So next we're going to talk about some definitions. So the empirical formula is the lowest whole number ratio of a compound. So if you have something like CH2 H2O. This is going to be the holeless this is going to be called an empirical formula because you can't divide the subscripts anymore because they're in the whole number ratio. And when we calculate the mass of this, so let's say that we just found the total mass of all the carbons, all the hydrogens, and all the oxygens. When we find this, what's going to happen is that we're going to find the empirical formula mass. On the other hand, if we have the molecular formula, which is not the whole number ratio, so in this case, C2H4, and then O2. Notice how when we multiply this number by 2, we get C2H4O2. And since that's not in the the lowest whole number ratio of the compound, we say that it's the molar mass. So we can actually convert between these two. When we take the molar mass, which is the mass of this, and then the empirical formula, the empirical formula mass of this, we get, and you divide those numbers, you get this number 2. So to essentially get to this molecular formula, what you do is that you just multiply the CH2O by this factor of n, which is 2 in this case. And we'll do some more practice problems on this in the breakout room section. We can also talk about percent composition. And what mass percent is, or percent composition, is that the mass of the element in 1 mole of the compound over the molar mass of the compound. So for instance, if I wanted to find the percent composition of, let's say in this molecule FeCl3, the percent composition of the iron in FeCl3 would just be the mass of the iron over the total mass of the compound, which is just the iron times the 3 chlorine molecules. Likewise, if we wanted to find the percent composition of Cl, we just take the mass of 3 of the chlorines, because there are 3 of them, over the total mass, which is just the 3 chlorines plus the iron times 100. You can actually use percent composition to determine the molecular or in the empirical formula. So what's going to happen is, in the problem, usually they'll give you like the percent composition. So they'll give you, say, like 40% iron and then 60% like chlorine or something like that. And then you can go ahead and actually turn that into its empirical formula. I've listed out some like the rough steps here, but we'll actually go into more detail in the practice room. So essentially the steps are, you assume that you have 100 grams of the substance and you turn percent comp into the grams. So you can say it's 100 grams because just think of it as like, oh, it's the whole part. So if you have the whole 100 grams, if you divide it into these elements into certain percentages, you can equate them into the respective grams. So what this means is that in this compound, going back to this example, if I have 40 Fe, if it's said in the problem I have 40% Fe, you can say that's like 40 grams. And this is not actually the percent composition of Fe and FeCl3. I'm just making these numbers up. Similarly, if I have 60% sealed, you can just say I have 60 grams of Cl. The next step is that you turn each quantity of grams into a mole. So you would just divide by the number you find in the periodic table for these elements. And then the third step is you divide all the numbers by the smallest number found in step 2. Sometimes when you do this problem, you'll get around a half number, like say 3.5. So what you want to do is you want to turn it into a fraction and then multiply it by the denominator so that you can, make that fraction not a fraction anymore. And we'll get into more detail when we do the practice problems. And then next you just write the formula. Okay, so that is pretty much all of the lecture section for this review. And we'll take a quick 5-minute break. And then after the 5-minute break, we'll break out into breakout rooms and then do practice problems. So if you have any questions, feel free to ask in the chat in the meantime. But we'll see you around 11:40 and we can go ahead and do those problems then.
Okay, so we are going to start our breakout room portion, but we're going to just stay in the main room. I'm going to go over the problems for chapter 4, and Jeffrey will go over the problems for chapter 5. So if you all have any questions, feel free to unmute, or you can put in the chat and our supporting leaders will clarify accordingly. So let's go ahead and get started. So like we discussed in the lecture portion, one of the main topics is effective nuclear charge. So how does the effective change going across these elements? Does it increase or decrease? Yeah, so obviously Z effective increases, right? So I'm going to use a different color. Increases as we go across the period, and what happens as we go down the group? Decreases, perfect. So understanding atomic radius and ionization energies, let's go ahead and rank the following atoms from largest to smallest radius. So, and then we'll look at highest to lowest ionization energies. So looking at atomic radius, what will be the largest? The largest element out of CR and CO. So if we look at, we have Br, Ga, Cr, and Co. So remember, as we go down the period, the atomic radius decreases. So the largest one would be the furthest towards the left, right? Does that make sense? Okay, awesome. One second. Okay, so our ranking would be CR would be the greatest, CO, GA, and BR. So for ionization energy, I'm just going to abbreviate it as IE. What will be our ranking? What will have the highest ionization energy? Perfect, BR, right? Since it's the smallest, it will have the greatest effective nuclear charge, meaning there's greater attraction, so it's going to be harder for me to remove that electron. So it'll be BR has the greatest ionization energy, GA, CO, and CR. Similar example, ranking these elements from largest to smallest radius and then highest to lowest ionization energy. So if we look at atomic radius, what is the largest in this set? Perfect, FR. So we can look at the periodic table as well. We have FR, CS, NA, and RB. So they're all part of the same group. And so further you go down, the greater valence shells, so increasing in size. So FR is greater than CS, greater than RB, is greater than NA. Knowing this, how do we, which one has the highest ionization energy? Perfect, yeah. NA is, so it's a complete opposite, right, of radius ranking. Perfect. Awesome. So let's keep going. So understanding ionization energy is very important. So this is a chart. There's different ways you can be presented ionization energies. Sometimes based on PLTL packet, you'll be given This is ionization energy 1, 2, 3. And then, for example, I think magnesium was the example. Mg becomes Mg plus an electron that's lost. And then this is the ionization energy. Versus another format that you can be given ionization energies is in a table format. So we have a couple of elements here. This is first ionization energy, second, third, fourth, and fifth. So we're particularly looking at boron. So boron. We want to explain these two observations. The ionization energies increase with each successive electron that is lost. So why is that? Why does the ionization energy increase with each successive electron that is lost? So for B, first ionization is 800, but second ionization energy is 2426. So why is it increasing? Perfect. Yes, so ionization energy is the amount of energy needed to remove an electron, and it takes more energy to remove electrons. Why? Because with each electron that's lost, there's greater effective nuclear charge, there's greater attraction because there's more positive charge now than electrons. So because there's greater attraction, it's going to be harder for me to remove another electron. So that is the explanation for this first observation. For boron, IE4 is much larger than IE3, IE2, and IE1. So IE4 is 25,000 something versus 3,000, 2,000, and 800. So why is particularly ionization energy 4 so much higher? What is the reasoning? Taking out from a noble gas configuration. So we are looking at boron, right? Is boron a noble gas?
What I was trying to say was that when you take the 3 electrons, right, you essentially make it so that it has a noble gas configuration of like helium. So you take out 3 electrons, then you take out another electron, and then you're taking it out of that stability. Does that make sense?
Yes, I understand what you're saying. So, and you're on the right. You're exactly correct. So remember, boron has 3 valence electrons, right? So after the first, second, and third ionization energy, meaning you've removed the third electron, which is the third of the valence electrons, you're now in the core shells. So, which is very similar to a noble gas configuration, it's completely in an octet. It's much harder for me to remove electrons that are no longer valence, but now core. So, because it's more closer to the nucleus. Thus, the ionization energy, meaning the energy required, is going to be much larger because I'm removing from not a valence shell, but a core shell. Awesome. So main thing here is understanding what element am I looking at and what is the valence electrons there. So if I have a different element, for example, magnesium, after ionization energy 2, the third one would be the one that's extremely high because I've taken 2 of the valence electrons out. So be aware of what element you're looking at. Okay, so let me make this smaller. So by looking at the electron configurations of elements, can you predict which element has the lowest first ionization energy? Which one is it? D, right? So main thing we want to look at here is what element are we looking at? So given the electron configuration, we can know what element what element this characterizes. So 3s1 is, yes, 3s1 is Na, right? So the other ones ends in 2p6, 2p4, 3s2, and 2p5. So 2p6 is over here, 2p4, 2p5, and then there's 3s2 and then 3s1. So remember, further down we go, meaning down the period, increase in valence shells, increase in shielding, so decreased effective nuclear charge, decreased attraction, so it's going to be easier for me to remove that electron, meaning lower ionization energy. So I want to be large, right? I don't want to be a really small atomic radii, but lots of shielding and not that big of a radius. And in this row, it's going to be Na. Does that make sense? Oh, why Na and not Mg? So remember, as we go down the period, atomic radius decreases because we're adding valence electrons to the same energy level. Meaning, for example, this one, we're adding electrons to energy level 3, but we're increasing the number of protons. So there's greater positive charge. Yeah, okay. There's greater positive charge, so there's greater attraction, but you're only adding the negative charge at the same distance. Okay, so good question. Low first ionization energy is considered a property of metals or nonmetals? Perfect, metals. And we just saw that, right? Na is a metal versus nitrogen or oxygen nonmetals. So everything over here has very low ionization energy, not that big of a radius. So this is metals. Okay, ionization energy is the ability to capture an electron, true or false? False, because what is the ability to capture an electron? What is this definition for? Electron affinity. So it actually is false. Ionization energy is energy required to remove an electron, not gain one. Ionization energies and electron affinities are which of these? Okay, so you have C. Anyone agree, disagree? So are they inversely related to each other? Yeah, so they're actually similar trends. They're actually similar trends. So one thing that is very important, just like test taking tips, inversely and indirectly mean the same thing, right? They're both, as one goes up, the other one goes down. So if you have two options that are the exact same, neither of them are going to be the answer. And dependent upon each other is a very vague answer, right? So if we look at this as we go down the period, decrease atomic radius, increasing ionization energy, meaning it takes a lot to remove an electron. So it's more easier to capture an electron because there's increased effective nuclear charge, there's increased pull, there's increased attraction. So they're both directly related to each other. And we can, if we look at this chart, IE and EA are both the exact same. They're both high as you go all the way diagonal. Okay. So electron configuration of ions. So can you guys tell me what is the electron configuration of? Yes, so ionization energy is the energy required to remove an electron versus electron affinity is the ability to gain an I think one of the supporting leaders can also add on to this explanation. Okay. So can you guys write for me the electron configuration of Cu and Cu+? We know that Cu+ would be smaller. That was one of our examples. So Cu, perfect. We have it already in the chat. 1s2, 2s2, 3s2, 3p6, 4s1, and 3d10. So how is Cu+ going to differ? Perfect. So you're going to be removing an electron from, perfect, yeah, from the 4s orbital. 3s2, 3. So Cu+ with me. So yeah, perfect. You guys have it correct. Go ahead and do it for Zn, zinc, and okay. So for Cu+, so it's right here, right? So it would be, let's say we're starting at the noble gas argon, 4s2, and remember these d orbitals will be one level down. So if this is 4s2, so it'll be 3d. Technically this is 3d9, but we need the d orbitals to be completely filled at this point. So we're going to take one electron from this 4s to where we complete the 3 ds. So it'll be 3d10, 4s1. Does that make sense, Michael? Yeah, awesome. Yeah, there's a great explanation from Jeffrey as well. So I'm going to, yes. So it can be more stable. So 1s2, and we already have Zn over there. So can y'all put zinc 2+ as well? What did y'all get for zinc 2+? Perfect. Yeah, so if we were to put this in shorthand, what would it be? You guys have the correct answer. So your answers are completely correct. So Zn, if I'm putting it shorthand, it would be argon, 4s2, 3d10, and then obviously Zn 2+. I'm going to be losing 2 electrons because it's a cation. And those 2 electrons are going to come from the outermost shell, which is the 4s2. So I'm left with this. Perfect. Awesome. You're good. Yeah. Alright, so ion radius. We're going to list these ions from smallest to largest. So go ahead and give me the ranking. Which one would be the smallest? Okay, so we want to look at, so we know cations are going to be small, correct? Because you have lost electrons, there's greater effective nuclear charge, there's greater pull, decrease in radius. So Zr4 plus is extremely small because it has a 4+ charge. So that would be your smallest ion. And then you're differentiating between K plus and Rb plus. So K plus is over here, Rb is over here. Which one's smaller, K plus or Rb? So remember, as we go down the period, the atomic radius increases as we go down because you have greater shells. This has 4 valence shells, this has 5 shells. So K would be smaller. So we have K plus next, and then what? Rb plus. And then you have your neutral. So I'm going to compare now with Mg and, actually I only have one neutral, which is Mg. And then I have 2 anions, Br minus and Se2 minus. So which would be smaller, Br minus or Se2 minus? Perfect, Br minus. So the greater number of gain of electrons, less pull, less Z effective, less attraction, so decrease in radii. So this is Se2 minus. Awesome. Any questions on this? Okay, so main thing is, remember cations are very small. You're removing electrons. Anions tend to be larger in size. You're gaining electrons. Okay, Lewis dot symbols for C, S, and I. So main thing here is understanding the number of valence electrons for these. So what is the valence electrons for C? Perfect. And then S. Awesome. And then F. Perfect. And then when you draw it, I'm sure you guys are familiar, it would be something like this. So, 1 second. The element, I think it's supposed to be F, but F and I are both 7 valence electrons, right? F and I are both 7, so they're both halogens. So they both will have similar valence electrons. Okay, so main thing is, if you have C, remember 4 valence electrons, so this would be your Lewis dot structure. And then for S, we said it has 6, so 1, 2, 3, 4, 5, and 6. And then for F, we said it had 7, so 1, 2, 3, 4, 5, 6, and then 7. Okay. Okay, last part is identifying what kinds of compounds these are. So ionic versus covalent. So we have 4 here. NaCl is what kind of compound? Ionic, because it's a formation between metal and non-metal. Perfect. What about AlF3? Ionic. And then SO2? Perfect. And then Pi3. Awesome. Awesome, awesome. If y'all have any other questions on these topics, feel free to put it in the in the chat. So those are my questions. So I'm going to stop sharing. And Jeffrey, if you want to go ahead with yours.
Sounds good. 1 second. Let me go ahead and share my screen.
Yes, sure.
Okay, cool. So this is going to be my second half of the practice problem. So I'm going to go ahead and we can work on this together. So part 1 asks us to identify the type of bonding present or the type of compound in each compound and provide them with a proper name. Okay, cool. So let's get started. So on our test, what I like to do when I tackle nomenclature problems is to identify first what type of compound it is. So what's the difference between ionic compound and then nonmetals? And then ionic compounds and covalent compounds. Cool. Yeah, so ionic is transfer while covalent is sharing. Good. So ionic, like was mentioned, is a transferring of metal and non-metal, right? And then covalent, yeah, also covalent does not. So we can say that the covalent is between non-metals. Okay, cool. So let's get started. Using those tips we have in mind and the rule we talked about last time, let's talk about A. So what type of bonding, or what's the type of compound in FeBr3? What do you all think? Yeah. Yeah, awesome. So the first one would be iron 3 bromide. Iron 3 bromide. And the type of bond present is going to be ionic compound. So the next problem, CCl4. What do you all think that the correct name for this is, or the type of bonding that's present? Yeah, so the correct answer is carbon tetrachloride, because notice when we have two nonmetals, you want to add the prefixes into them. So for instance, because this is a covalently bonded compound, you want to name first the carbon, and then you want to name the chlorides, but also you want to add the prefixes in front of the Cl, because this is the rule for naming covalently bonded compounds. Awesome. Yeah, of course. So a little hint I like to give you is that when you see a metal, usually you want to not put the prefixes. So you say, like, we didn't say that it was iron, like tribromide. No, we didn't do that. Yeah. This is covalent. And what about this one? What about the third one? Yeah. So dinitrogen pentoxide sounds correct. And why do we get rid of that O in the second one, you may ask? Well, it just sounds more clear. So you want to say pentaoxide. Notice how there's like kind of a guttural sound, but just to make it smooth and crisp, you say just dinitrogen pentoxide, which is awesome. Good job, you all. Next, let's go on for that. Cyanide. And then what type of bond is this, or what type of compound is this? Beautiful. So let's talk about this one. So let's figure out what kind of this is. What kind of compound is this? Sodium perchlorate. Yeah, sodium perchlorate. So why isn't it just sodium chlorate? What would sodium chlorate look like? CO3, yeah, so ClO3 minus is chlorate. So yeah, these are awesome answers. So you have ClO3 has 3 oxygen, it got added 1 more, perfect. Cool, excellent. So sodium chlorate would look like NaClO3. And yeah, and so what kind of bonds do you think are present between, or what kind of compound do you think it is? Ionic, yeah. And why is it ionic? Yeah, metal and non-metal, perfect. So this one, yeah. So the ClO4 has a minus charge on it, right? Has a minus charge on it. So, and then this one has a plus on it when you break it up into its constituent ions. So because they have to share it, I mean, they have to transfer it. That's why, it's going to be an ionic compound. Excellent. Okay, so let's talk about this one. So is this one iron 2 sulfate or iron 3 sulfate? What do y'all think? We have 3, we have 3. Oh, okay, so why isn't it iron 2 sulfate? But isn't there like a 2 right here? Yeah, that's sulfate's charge. Beautiful. Yeah, the cross thing that I talked about. Perfect. Yeah, so good catch. So I like that you guys, crossed it. So we write Fe, right? And then we do SO4, right? This one, this charge will go to that one. And then this one will go to that one. And that kind of makes sense because sulfate, we know that it has a 2 minus charge. So it makes sense that it's going to be iron 3. Perfect. Excellent job, you all. So I'm going to say iron 3 sulfate. Cool. So let's do the first one. HBr. What is HBr in the aqueous state? Hydrobromic acid. Perfect. Yeah. So because it's in aqueous and it has a hydrogen in front of it, we're gonna name it as hydrobromic acid. Hydrobromic acid. Okay. So let's do the second one. What about HBr? Hydrogen bromide for salt. Perfect. And so for this one, the type of compound it is, well, the HBr aqueous is gonna be an acid, and this one HBr, what is it gonna be? Is it ionic, covalent, another acid? Oh, it's a typo. Good catch. Yeah, it's just a typo. This one should be capitalized. Covalent. Yeah, perfect. I mean, actually, so let's think about it, right? We have a Br minus. Okay, so there are a few questions here. So why did you add ic instead of us for the acid? So if you refer back to the chart, we only use ic and the us for the sulfates or like the eights. So if you have a polyatomic ion that has an 8 in it or an ite, you use ic or us. But if you just have its one element, if you're making an acid out of one element, it's just going to be the root work. So the root of the element, which is in this case it's bromic, it's brome because it's a bromine. So you add the words hydro and the last ic in front of it. You put the hydro as the prefix and then the ic as the ending. Does that make sense? Yeah, perfect. Like that was mentioned, hydro root ic and that's for singular elements. Yeah, awesome. Good question. So for this one, I would say that HBr is actually going to be ionic because notice how you have a Br here, which is minus charge, and you have this H here, which is positive. So to get Br to have 8 electrons, H is going to transfer. Okay, cool. That being said, let's move on to the other ones. So this one, and this one. So with that being said, how come did you not write mono at the end? So the reason why I didn't write mono at the end is because we name it as a ionic compound, right? And with ionic compounds, you don't use prefixes. Does that answer your question? Okay, cool. So let's move on to the next one. So in the meantime, HClO4. If you don't have the state specified, what type of compound is it? So if we have an H in front of it, right? And there's no indication of solid or aqueous, acid aqueous. Perfect. Cool. Okay. So we can say that it's an acid. So how do we name this acid? Perchloric acid. And so what about HClO2? So we have an answer of chlorous acid. So let's think about it, right? Let's go ahead and just write out the forms of CO3. How do we know it's an acid? Well, when I took this class, when you have an H in front of something that doesn't have a state in front of it, you can automatically assume that it's aqueous. Your professor might do something different, but that's kind of the rules that I go by. So moving on to the naming of the H, right? So what is chlorate? What's the formula for chlorate? Okay, yeah, so that's CO3 minus. Perfect. So what's one more oxygen above it, or like more of it? What do we call that? Some more? Yeah, so one more is going to be ClO4. This is going to be per. This is going to be 8, right? No, you're good, yeah. And then what's one less than the chlorate? Chlorite, perfect. Okay, so we do that. Exactly. So let's say, so what can we name HClO2 minus? Yeah, hypochlorite ClO. I didn't even ask for that, but you're on the track. You're on a roll. So this is going to be hypo and then I. Perfect. So with that being said, if we have an ite form of the polyatomic ion, what ending do we use to make it? Yeah, us. Perfect. Excellent. Hypo. Okay. So for this one, we can say that this is going to be chlorous acid. Chlorous acid. Okay. So let's talk about H2SO4. What would that look like? So let's think about it, right? We have SO4, right? We have SO4, which is what molecule? We have dihydrogen sulfate. So SO4, yeah, so SO4 is going to be a sulfate, right? So this is going to be a sulfate, right? So when we're finding acids of, yeah, SO4 2 minus, perfect. Forgot to write the 2. Thanks for catching it. So when we have a sulfate molecule, how do we form acids out of that? Yeah, so when we add hydrogens to it, what is the name that we should give it? 8 to sulfuric. Yep, perfect. So this is going to be sulfuric acid. So I wanted to point out something here. So notice how this is going to be SO4 with the 4 is going to be an 8, but down here with the chlorate, the 4 is going to be per. So each of them is a case-by-case basis on what's 8 and what's, per or ite. You can say that. So it's really important that you go and memorize all of these molecules. Okay. Yeah, good job. Good job, y'all. Does anyone have any questions? Cool. So if no questions, let's move on. So part 2 says spot any errors in the nomenclature and correct them as necessary. Okay, so C4O2, the name is carbon tetroxide. Is this correct or is this incorrect? CO4 carbon tetroxide? Yeah, so CO4 is carbon tetroxide. So what would C4O2 look like? What do we have to add or remove in this case? Tetracarbon dioxide. Perfect. Yeah. So this is going to be tetracarbon dioxide. Carbon. Perfect. How about the second one? Barium dihydroxide. Is this correct or is this incorrect? Yeah, so it's just barium hydroxide. Perfect. Because notice that we have a metal here and we have a hydroxide, so this is a minus charge, and this is going to be has to be a plus charge then. So we can say that when we have a form of ionic bonding, what we do is that we label it without prefixes. So the prefixes are wrong here. Perfect. And what about this one, the third one, F3Cl2? Is this going to be correct or incorrect? Correct. Yeah, perfect. So this is correct because it's a covalent bond, so we just name the prefixes and we name the elements. Awesome. So what about the fourth one? Okay, we have an answer for incorrect. What does everyone else think? We have phosphoric acid as an answer. Do we all agree? Yeah, so this is going to be actually phosphoric acid. Perfect. Phosphoric acid. Excellent. Do we have any questions on this? If not, then we can go ahead and keep going. Okay, so now we're going to transition. We're going to do a lot more math. So if you'll have a calculator and a piece of paper out, feel free to take it and work along with me as I go through this problem for you all. Okay, so fill out the following table. So we have molecular formula, empirical formula mass, and molar mass. Okay, cool. So let's start with this problem, right? So when we find the total grams of the empirical formula, what quantity does that give you? Does that give you the empirical formula mass, or does that give you the molecular formula mass? I mean, or the molar mass. What does that give you? So when you find the mass of this, what is this called? Is it the empirical formula mass or the molar mass? So when we find the mass of the empirical formula mass, it's going to give you the empirical formula mass essentially. So what we do is that for CH, just add them up, right? So CH is 12 point, carbon is 12.101, and then H is just 1.01. So what does that give you? 13.02. Perfect. Okay. Now we're going to have to find the molecular formula. So if you remember from the PowerPoint, how do we convert the empirical formula to the molecular formula? Like, what number do we have to multiply by? What is that number or letter called? N, right? Yeah. So how do we find the N in this case? Yeah, 78 divided by 13.02. That's perfect. So let's do 78 divided by 13.02. And what number do we get? 6. Perfect. So how do we get to the molecular formula in this case? Multiply by 6. Perfect. So when we multiply by 6, we get C6H6. And that's your answer for this one. Any questions on that? Okay, cool. So we have a molecular formula right here in the second problem. If we have a molecular formula, what can we multiply these numbers by? I mean, divide these numbers by? 2, right? So when we simplify it, or we divide by 2, what do we get? CH3. Oh, perfect. So how do I find the empirical formula mass for CH3O? Do we find the mass of the molar masses for each element? C12.01. Yeah. So essentially, what numbers are we going to calculate for the empirical formula mass? Do we use this formula or do we use this formula? Oh yeah, I think someone's writing in the chat too. Awesome. That's 12.01, right? The empirical formula, right? Plus 3 times 1.01, and then plus let's call it just 16 for oxygen. So I want you all to try this yourselves and let me know what number you get. Yeah, 31.02. Perfect. Did everyone get that? Yeah. 204. Yeah. So yeah. So 31.04. So how can we find the molar mass? So do we find the mass of this or this? Yeah, essentially, just multiply by 2, right? So what would that be? Yeah, perfect. Or what you can do is you can also just take 2 times the individual elements here for the molecular formula, and then get it to molar mass. Cool. So let's think about this one. So the last one is CuNO2. So with that being said, if we have an empirical formula, what can we go ahead and find? Yeah, empirical formula mass. So let's go ahead and I'll give you a second to calculate. See, so we do, let's see. So according to my periodic table, we just take 63.54 plus 2, right? Because we have 2 nitrogens, because look, when you spread it out, you gotta like distribute that, right? So 2 times what? What are we taking 2 times by for the nitrogen? 14, perfect. So we have 2 times 14. And then how many oxygens do we have? 4, okay, so we have 4, excellent. and then we do 4, and then the mass of that 16 of the oxygens. So what is our final answer for the empirical formula mass? $155.54, correct. Okay, so 155.54. Okay, so 155.54. Okay, so there are a couple of blanks here, right? So notice how we don't have a molecular formula or a molar mass, right? So in this situation, what's going to happen is that because we're missing these two pieces, we can assume that the molecular mass is going to be the same as the empirical formula mass, because they don't really give us information, right? Because if they give us molar mass, we can divide to find molecular formula. But since they don't give us that information, we can just say that this is going to be the same. So if it's the same, so what would be the molecular formula here? If it's the same. Same as empirical. Perfect. Awesome. That can be a bit confusing. So does anyone have any questions on this before we move on? Or want me to explain that again? How can we assume molar mass is the same? Well, in this situation, we said that it's the same because they didn't give us any information of molar mass or molecular formula. So we can assume that, remember how we had to find the n, right? We have found the n is 6 here. So in this case, n is 1. Because what happens when you do this? 154 over 154? You just get 1. I like this topic. Yeah. It gets pretty math intensive as you take more chem. So it's really good to build these foundations. Yeah. Okay, cool. So that's a good question. Now let's move on to the next part. Okay. So calculate the percent composition by mass of each element in phosphoric acid. Okay, so there are 2 problems hidden in this one. So we don't know what phosphoric acid is. So who can give me a formula for phosphoric acid? Oh, can you just go up and screenshot it? Yeah, sure. So I'll go ahead and scroll up here. This will also be posted on the SSC website, the YouTube channel. So you can also refer to the key that will be posted on here, or watch the video recording. Yeah, of course. Okay, so let's find the percent composition by mass of phosphoric acid. Yeah. So we have an answer, which is H3PO4. So do we all agree with H3PO4? Yeah, so just for the sake of time, it's going to be phosphoric acid, so it's going to be H3PO4. So why do we have 3 hydrogens here? Well, if you think about it, PO4 is going to be 3 minus, and then you need 3 H's to balance it out, so you just put 3 positives here. Okay. Cool. So how do we find the molar mass? Let's start with the mass, right? The mass of the entire molecule. So what is the mass, or how do you find that? So just for the sake of time, we're going to take just 3.01. That's going to be 3 times 1.01 plus the P. So P in this case is phosphorus, and it should be 30.97 grams. And then we have 4 oxygens, right? So we take 4 times 16. And when we have this, when we add up all the grams, we get 98 grams. So finding each element in phosphoric acid, we have to do it for H, and then we have to do it for O. Let's just go with P because it's next in the list. And then O. Okay, cool. So with that being the case, when we do that, we have to take the mass of hydrogen. So this portion, right, goes there. And then we take the total mass, which is 98, times 100. And then for P, same thing. So we take this entire thing, put it here, and then over 98 times 100. 100. And then O, same thing. So this part, 16 times 4 here, and then we do 98. So does anyone have any questions so far on like how I got these calculations? So you can think of it as like a fraction, right? So it's the fraction part of H over the total, fraction part of O over the total, fraction part of P over the total. Yeah. So with that being said, just for the sake of time, I'll go ahead and give you the answers. But I highly recommend you doing this, going back and doing it on your own, just for that practice. So for H, we get 3.08%. We get for P 31.6%. And then for O, we get 65.3%. Okay. Anyone have any questions on that? Yeah, so just, calculations. Cool. So if not, then let's move on to this problem. This one can be a lot, so we'll go through it together slowly, so make sure you guys get the concept. So the percentage composition of acetic acid is found to be that carbon, that hydrogen, and that percent oxygen. Determine the empirical formula of acetic acid. And the question also asks, what is the molecular formula if the molar mass is 60 grams? Okay, so what is one assumption? Oh, for hydrogen, did you use 3.03 or 1.01? That's a good question. So you can go here. Notice how it's the fraction of total hydrogen over the total mass, right? So you want to account for all those 3 molecules of hydrogen. You can't just include one when there are 3 of them, Yeah, does that make sense? Yeah. Yeah, thank you for answering their question. Awesome. Cool. Okay, so going back to this problem, when we have a percent, if you remember from the lecture, what amount of grams can we assume that there's total? 100. Perfect. Cool. Great. So we assume 100 grams. So if we have 100 grams, right? And that's part of the 100 grams carbon, that part of the 100 grams of the hydrogen, and that part of the grams of oxygen. How many grams of carbon, hydrogen, and oxygen would there be? Yeah, so like was mentioned, 39.9 grams of carbon, 6.7 grams of hydrogen, and 53.4 grams of oxygen. Perfect. So let's say that we have 39.9 grams of carbon, and then 6.7 grams of hydrogen, and then we have 53.4 grams of oxygen. So with this being said, what is the next step, if you'll remember from the PowerPoint? What do we have to turn these numbers into? Yeah, perfect. I turn to moles. Because what moles do is that they are like the basic unit of comparison. Because we can't compare these grams by itself, right? We have to change it into moles. So what do we have to do? What number do we have to divide by the molar mass of each element to convert each element to moles? Perfect. So when we divide that, as mentioned, we just divide by 12.01 times 1 mole. This is gram. And then for this one, we have 1.01. And then we have 1 mole. And then we have, for O, we have 16 grams. And then we have 1 mole. So just for the sake of time, I'm going to go ahead and just, plug these numbers in for you all into my calculator. And the numbers I get are, and feel free to do this if you have a calculator nearby. But so just pulling up my calculator, the numbers I get are approximately 3.323 mole of C, right? And then we have 6.633 mole of H, and then we have 3.33 approximately mole of O. Does anyone have any questions on how I got these numbers? Does the instructor prefer we use 1.01 or over 1.008? The periodic table that your professor gives you, I would follow that instead. So the periodic table that I used, I got 1.01. So, okay, yeah. Yeah, of course, that's a good question. And so notice how I'm not rounding intermediately, right? So these are the numbers that I appeared on my calculator. So just for precision, save your rounding until the end. I think that's one tip that will take you a long time, even through Gen Chem 2, is that when you do these numbers, you always want to round at the end, not round in between. Those are some, test taking tips I can give you. And what is the next step that we have to do, if you remember from that PowerPoint? If you don't, then that's okay. But does anyone remember? Divide by the smallest. Perfect. Close. So we're gonna divide by the smallest. So, what's the smallest number here? Yeah, 3.33. Yeah, so 3.323. Yeah. So the reason why we want to divide by the smallest number is that when in an empirical formula, we want to find the smallest whole number ratio, right? Because that's what an empirical formula is. And we do that by making these numbers super clean by dividing by the small number. So when I divide this, I get C is just 1, H is going to be 2, and then O is going to be 1. And you know that you're doing something right when these numbers are crisp and clean like this. So that's one thing, but another tip I can give you. So we have CH2O. Does anyone else have any questions? This kind of makes sense. Oh wait, actually, pretty clear. Good. Are we good? CH2. Oh, yeah, perfect. So yeah, so I'm running the one to show you all that. We got one. Yeah. So just the C1, as I'm gonna show you just for clarity. Yeah. So for people watching at home, they kind of know where I got these numbers from. Yeah. So if we have this, right, if we find the mass of this, what is it called? Empirical formula mass. Yeah. And so and then my next question was, how do we find the mass of that? Which was, yeah, if it's okay to round, if it's a closer number. Yeah. So if it's let's say 2.9999, you can just say it's 3. Or 2.988, 2.889. And this step, it's good to round. Does that answer your question? So if it's a negligible number, like if it's 0.1 or 0.2 off, you can go ahead and round. But yeah, it's a good question. So as was mentioned, when we find the mass, we do 12.01 plus 2 times 1.01 plus 16. And what do we get? As around 30 grams. Is that what everyone got to? Yeah, so it's around 30 grams. 30 grams. Perfect. So this is one part of the problem that we found, and it also asks us, okay, we found the empirical mass, right? So we have the empirical formula mass, form mass, right? And in this problem, we are given in the problem that the molar mass is 60 grams. So what do I have to do in order to find, multiply by 2 so we can get the 60 grams? Yeah, perfect. So how did you all get the 2? So how did y'all get the 2 in this case? Yeah, 60 divided by 3. 30, right? Because if you remember that formula we did earlier, the N formula, so the molar mass over the empirical formula mass, just get 2. So take the original one and then times 2. So it's not, yeah. So it would be C2H4O2. Excellent. Okay, then that's kind of the problem. Does anyone have any questions, or did you all get lost somewhere? If you did, then we could go back and run through it. No? Okay, cool. So I know this is a lot, but if we get some good practice in, we have another problem too, and we can work on that together. Okay, so this problem, similarly, if the percent composition of pyrophosphoric acid is blah, 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 and the remainder oxygen, find the empirical formula. If the molar mass of this acid is that number, what is the molecular formula? Okay, so in the remainder oxygen, let's go ahead and try to find that. So what would the remainder oxygen be in this case, if we're given the two other percentages? What do you all think? 100 minus the others. Perfect. So when we 100 minus the others, what number do we get? So just to do the math for you all, I get 53.4. Okay. And our first step, if you remember from last time, oh, actually, no, I got the wrong number. Sorry. I was looking at the previous problem. It's going to be 63.2. Excuse me. 52.93. Yeah, perfect. And so first we assume 100 grams, right? That's our first step. So assume 100 grams. So like last problem, if I assume that this is 2.27%, we have 2.27 grams. If we have the phosphorus, it's 34.8 grams of phosphorus. This is for H, let me write that. And then we have the remainder oxygen, which is 62.93. Okay. Right. So did not mean to do that. And so our next step, if we all can recall, what was our next step? 1 over mass. Beautiful. So to do that, 1 over 1 mole over 1.01. Dimension analysis will cancel this out to get you moles for P and then for O2, for O as well. And so the one for P is going to be, what's it called? Is going to be 30.97, according to my periodic table, 30.97. And then 1 mole. And then for O is going to be 16. And when we do some division, what we get is we get let me go ahead and plug that number into my calculator. We get, so my biggest tip here, like I mentioned, write out every number you get on your calculator. Don't do any intermediate rounding. 1.1235 mole of that, mole of P, and then mole of H, and then we have 3.93 mole of O. 3.9333 to be precise. Okay, does anyone have any questions on how we get these numbers? Okay, if not, so if we don't have any questions, what is our next step? What do we have to do next? Divide by 1.1352. Yeah, so like I was mentioned, we divide by the smallest number. So the smallest number would be, in this case, 1.1352, 1.1352, and then 1.1352, 1.1352. Okay, so this next step is very important, so I want y'all to do it. So when you plug in these numbers into your calculator, read for me what numbers you get. So we have HPO, right, after we divide. So I'll give y'all like a few seconds to do this at home, and then let me know the numbers once you divide by that small number. Yeah, H is 1.979, so we can assume that's 2, okay? We can assume that's 2. And what about P? P is 1 and O is 3.5. Okay, yeah, so P is going to be 1, right? And then O is going to be 3.5. notice how I'm going to write this in a different color because this is really important, right? Notice how we did 3.5 here. We didn't say that, oh, it's 4. We didn't say that it's 3. So if you get a number around like half, so like 3.4, like 3.6, you can go ahead and round it to 3.5. And does anyone have any questions on this? This is really important because we're going to have to do another step in order to get our formula. Is everyone kind of clear on why we do 3.5 instead of the rounding up to 4 or 3? Okay, pretty clear. Okay, cool. Yeah, sounds good. Yeah, so this is really important. So when we're talking about a compound formula, we're interested in whole numbers, right? And in this case, we don't have whole numbers. We don't have any whole numbers. So how are we supposed to cancel out that 0.5? Multiply 2 to get whole. Yeah, I like that idea. So what's going to happen is, notice how we get H2, right? P1, that's the same. And then O, that turns into a 7/2 as a fraction. And so, like in math, when you undo a denominator, what you do to it is you just multiply the numerator by 2. But in math, you do something to the top, you have to do something to the other parts. So multiply everything by 2. Okay, so in order to get that, we have H4P2 and then O7. Does that make sense? Does this make sense to everyone? Yes, perfect, awesome, good job, y'all. So this is the hard part. This is the hardest part. We made through it. So when we do the next part, is this going to be the smallest whole number ratio or not the smallest whole number ratio? What do y'all think? Not the smallest, right? So it's going to be not the smallest. And so when it's not the smallest, what is this? Wait, so is it the smallest though? Or is it not the smallest? How did you get that? Yeah, not the smallest. Yeah, it is, right? Because H4P2O7, can you divide by a common denominator in this case? No, right? Yeah, so because there's no common denominator, what's going to happen is this going to be a empirical formula, right? Because it's the wholest number, a small wholest number, so this is going to be the empirical formula, right? Because notice how we can't divide by like 2, for instance. Sure, the H is 4 and P is 2. They're divided by 2, but O is 7. We can't do that. We can't divide by 2. Yeah. So when we have an empirical formula, what can we find? When we add the masses, what do we find? Or like, is it the empirical formula mass or is it the molar mass? Empirical formula mass, yeah. So just for the sake of time, I'm going to go ahead and just do that for you all. So the way I would find this is I would take 4 times 1.01 plus 2 times, let me go ahead and fetch my periodic table really quickly, 30.97. And then we have 7 times 16. So when we do the math, we have 177.97 grams. So this is the imp mass. Okay. Okay. So now we have our problem is asking us to find the molecular formula. So how can we find the molecular formula in this case, given that we just found the empirical formula, S, and the empirical formula too? Yeah, it's the same as empirical, because in this case, right? Yeah, isn't it the same? Perfect. So in this case, notice how you want to do the molar mass, right? This is the molar mass, which is given the problem, and then we have this number, right, which we found down here. So this is another situation in which the molar mass is the same as the empirical formula mass. So N is equal to 1. Let me just do this in a different color so that you guys can follow along. And this one, therefore, the molecular formula is the same. Okay, and that's the end of our problem solving session. Does anyone have any questions? Yeah, so since that's the end, Good luck on your exam. Thank you so much for you all for being here on a Saturday morning. If you have any questions, we can stay back and talk about these questions. But other than that, we all wish you good luck on your exam. Yeah, just gotta practice more. Yep, that's the key. Alrighty, y'all take care. Good luck.